Let's go ahead and get started. I see you all have glum faces. I know you're all bummed out because this is our last class for the quarter. Me too.
I'm sure you're the happiest one.
I'm the happiest one? No, I like this. It's fun for me. It doesn't maybe look like it sometimes, but it is. Well, we'll see each other again one more time next week. I wanted to start with a couple of announcements. So first of all, I already announced this last time, but I'll say it again. Please do share your thoughts about this course by filling out course evaluations. I can't tell who has done it, but I have been informed that only about a third of the class has done so far. So we'd really appreciate some feedback. And you have until Sunday night to do that. And at the very least, please just go through and give me grades. That's probably fun, giving your professors grades. We actually take those grades very seriously, so we appreciate your feedback. The second announcement is that now that you've all presumably done all the homework assignments, I can tell you that in computing your final grade for the course, I'm going to drop your lowest one. Everybody has a bad day every now and then, so I'm going to take your lowest score and remove it from the calculation of your final grade. All right? Okay, so now we're going to get to work, and there's three little miscellaneous items that I want to show you today. None of these are actually covered by assignments, but I hope that you'll find them sufficiently interesting that you'll tune in. So the first thing I want to do is talk about how you might use Mathematica to treat real data that involves repeated measurements, in which what you will actually report is going to be a plot of the average of each set of repeated measurements, and then put an error bar that represents the uncertainty, which we will indicate as the standard deviation. Okay, and it'll show a couple of little tricks, or remind us of some tricks for doing data manipulation in Mathematica. And then the second thing we're going to talk about is I'm going to just give you a very brief introduction about how you can use Mathematica to communicate with some databases that are available at Wolfram Research. And in particular, we'll look at some chemical data. And then the final thing that I'm going to show you is just a brief introduction to how you can look at, play with, access, download a multitude of Mathematica notebooks that are out there on the internet, and you can view them without actually having to buy the program. So I'm going to give you a brief introduction to that in case you found what you learned this quarter sufficiently compelling that you may want to learn more. The best way to learn more and do fancy things is to look at examples that do things you want to do. Okay, so that's the plan for today. And let's go ahead and get started. What we're going to do is we're going to import a file that contains data from the class website. Okay, it's lesson11.dat, so it's just several columns of numbers. I'll explain to you in a minute what it's meant to mimic, but let's go ahead and grab the web address here. Okay, we'll see. And then I'm going to import that. And I'm going to store it in a matrix called dataset. Okay, so that's going to be import, double quotes, copy my web address, double quotes, and bracket. And now I get all these data. And let's have a look at the data. So data set in table form. Okay. And it's got several columns here. Get rid of this thing. I'll make it smaller so we can see all the data. So what is this? Well, it can be pretty much anything, but what I tried to model here was we have several instances in time here, and this is in seconds, so a minute, 2 minutes, 5 minutes, whatever. And then each of these columns is meant to mimic the concentration in a patient's bloodstream in some units, whatever, measured at different intervals of time. Okay, so this would be, you know, like maybe what's called a pharmacokinetics study. You want to see how quickly the drug is dissipated by the person's body. Okay, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 patients, let's say. All right, and you can see in each case the numbers are kind of going down. Now, I'm supposing I went in the lab, I measured these data, I entered them into a computer file, and now what I'd like to do is I would like to report the average as my measured quantity. All right, so for each of these time points, I want to go through and calculate an average of a given row of data. Okay? And then what I also want to report is the variability in the data. All right? So notice these numbers are all, roughly 700, but there's a little bit of spread in those numbers from one patient to the next. And so what I'm going to measure that spread as is the standard deviation. So we're going to go through each of these rows. We're going to calculate the average and the standard deviation. And then what we're going to do is plot the average numbers at each point and put error bars on the plot that contain the show the standard deviations. Okay? So that's what we're going to do. It's going to require a little manipulation, and then we'll introduce you to one more plotting command in Mathematica. Okay, so let me zoom in here. So the first thing I'm going to do is define variables that tell me what's the length of this matrix and its width, if you like. Okay, so the number of rows and columns. So length is going to be equal to capital length of data set, and I can measure the length of the data set by just looking at one of the columns. So I'll look at the first column, and that'll be bracket, bracket, all, comma, 1, bracket, bracket. And then I need one more bracket. Okay, and then width equals length of data set, bracket, bracket, 1, comma, all. So this is going to measure the width of the first row, or the length of the first row, if you like. Okay, so then bracket, bracket, bracket. All right. Now what I'm going to do is I'm going to create a table that's going to have the right dimensionality to contain the process data. Okay, so the process data is going to consist of the following. It's going to have one column which contains the time points. It's going to have a second column which is the average over each of these. And then a third column is going to be the standard deviation. Okay? And so I'm going to create an empty table that has 1, 2, 3, 4, 5, 6, 7 rows, and then it's going to have 3 columns. And then we'll store the actual computed data in this table. All right, so I'm going to say processed equals, and then just create a table full of zeros. So table 0, and then we're going to say I goes from 1 to length, little length, and then j goes from 1 to 3. All right? And if you enter that, you see you just get a table of zeros. Okay. Now the next thing we're going to do is something we haven't done yet. This is a very simple example of using Mathematica to do what you might call programming. Okay, so I'm going to type this thing in, and then I'll tell you what exactly it is that we're doing. Okay, so we're going to use this thing called a do loop. So you start out by saying capital do, bracket, and then I'm going to format it here. So I'm going to put in a tab, and we'll say processed, bracket, bracket, I, comma, 2, bracket, bracket. So this is going to be accessing the second column of my processed matrix here. Okay, so that's going to be equal to the mean of data set row I, comma 2, and then if we put in double semicolons, this will go to whatever the next number we're going to put in, which is width. All right, so I'm going to go over this again in just a second. All right, and then we say bracket, 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 or no, bracket, bracket, and I am missing a bracket here. So we need one more here. Okay, and I'll put a semicolon, and then tab, and then we're going to say processed. Well, let's just mouse this in because it's more or less the same. All right, and then put it back, and this time it'll be the third column. Okay, and now instead of the mean, we want the standard deviation. Okay, so this is what we're calculating here is what's ultimately going to be considered to be our error bar. And normally when you report error bars, you might say plus or minus the standard deviation. Okay, so in fact the bar should be twice the size of the standard deviation. So let's put a factor of 2 in here. All right. Okay, now the next thing we do is we say I goes from 1 to length. Okay, and then we can put in a bracket to end. Oops, seem to be missing something here. Oh, I'm sorry, these are not supposed to be, this last one's not supposed to be a semicolon, it's supposed to be a comma. Okay, then we can put in a bracket, and then I'm going to look at processed in table form. Okay, so let's just go over this one more time because you haven't seen this. So what this do construct means, so what you have is do, bracket, some commands inside, and then at the end of this do loop, you give the range of a counter over which you want to do that. Okay, so what we're doing here is we're going to do whatever's in here length times, because I is going to be incremented 1, 2, 3, 4, etc. to length. Okay, now within here, I is being incremented. What we're doing is we're taking the ith row. Let's see ith row, second column of this process matrix, and storing within that the mean of our data set array for the ith row and elements going from 2 to width. Okay, so basically if I was 1, we would be taking the mean of all these numbers and storing them in processed 1, 2. Okay, the first row, second column. And then similarly, this line here does the same thing, but instead of storing the mean, it's going to store 2 times the standard deviation. Okay, so if we enter this, whoops. All right. The problem is I don't need a capital length here, I need a small length. Okay. And another thing that I haven't done yet is I need to say that, let's go here and say processed, bracket, bracket, all 1, bracket, bracket, equals data set, bracket, bracket, all, comma 1, because I want to put the time points in here. Okay? Bracket, bracket. Okay, so now what you see is we have this new matrix where here I have my time points, and then what these are is the average values over all the 10 patients of the concentration of the drug in their bloodstream at those various time points. And then this is 2 times the standard deviation. And this is exactly the form that we need the data in if we want to plot with error bars, because the command we're going to use is going to assume that this is x, this is y, and then this is the size of the error bar that's going to be drawn. Okay? So let's go ahead and plot it. Now, the error bar plotting is not part of standard Mathematica packages, so we need actually to load a package. And that package is called error bar plots. So we say less than, error bar plots, single backward quote, enter. And now we can use a command. It's very similar to list plot, except it's called error list plot. So we can say error list plot, and then put in processed. And what you see is we get a nice plot. We can put plot range arrow all to get that error bar not being cut off. Okay, so now we have at each time point the average, and then 2 times the standard deviation drawn as an error bar. And this is you would normally want to report data that comes from repeated measurements in a similar form, where you represent an average value as your actual reported value, and then some sort of measure of the statistical or the uncertainty of the measurement, which in this case we've used 2 times the standard deviation. Okay, and then, you know, we're not going to make this plot look fancy, but all the usual options that you have for customizing the plot, labeling it, it's all available in error list plot in the same way that it is with plot and list plot. Okay, so that's your little introduction to including error bars in your plots, in case you ever want to do that. Now, in the notes, there's a more sophisticated example, but it's not one that comes up very often. And I'm not going to go over it today, because I think it's just, you can look at it if you're interested. So sometimes you don't want to report average plus or minus standard deviation. Maybe you have some reason to believe that the error is different in the negative direction than it is in the positive direction, in which case the error bars have different lengths, uneven error bars. There's a way to plot that, and like I say, it doesn't come up very often, but in case you ever wanted an example, you can look at our notes. It requires a bit more sophisticated programming. Okay, now what I'm going to ask you to do is don't follow along with me, because the next thing I'm going to show you is how to access databases with Mathematica. And if more than a few of us are trying to do that at once, it's going to slow down the network and we won't be able to do it. Okay, so I want you to just watch. And there's examples in the notes if you want to play with this yourself sometime. But if we all do it together, we won't be able to do anything. Okay? All right, so the point here is that, and let's go ahead. I'll pull up some documentation here. If you want, you can look at the documentation. All right? And there's a whole section on what's called computable data. And you can see that there are a lot of data available here. So for example, geographic data, all right, weather data, astronomical data, financial data. Okay, these things are available. What I'm going to show you is some chemical data. Okay, so there's lots of things that you have access to that are available at Wolfram that Mathematica will communicate and grab those data for you and display them in your notebook with the appropriate commands. Okay? So this is what I want you to not follow along with as I show you just a couple of simple examples to give you just an impression of the sorts of things that may be available to you. Because sometimes you may be wanting to do work in a notebook and want some data, and it's kind of nice to be able to just have it all be pulled in to your notebook. Otherwise, you can go to the various resources that you learned about in the library lesson and, you know, grab the data there. Okay, so the series of commands I'm going to start with here fall under the chemical data system. Okay, and they all go like this. They start out with chemical data. Oops, I'm in the wrong spot here. Go down here. Chemical data, bracket, and then you put in some information. So in this case, I want to look at the molecule cholesterol. Okay? And if I enter that, you can see it takes a little time. This is why I don't want us all to do it, because if we're all going to the same server to get the data, it's just going to shut everything down. All right, so you see if I just put in the name of a molecule that Wolfram knows about, like cholesterol, I get a chemical structure. Okay. Now, there are different ways to display it. So for example, if I put in the option molecule plot and weight, I get a different representation, which is now what we call CPK model. And you notice you can orient it how you want in your notebook. And, you know, so it might be kind of nice if you're doing something to do with cholesterol that you may actually want to have a picture of it. Another way of representing, well, I can leave molecule plot. There's another way to represent it, which is called space filling molecule plot, which draws what we normally call sort of a van der Waals surface representation of the molecule, so you can see how it looks and how it would look in terms of its accessible surface, let's say. All right, so there's a couple of ways of installing and manipulating a chemical structure in your notebook. Now, suppose you want some information on the molecule itself and its properties. So this is just a picture. So for example, what's the chemical formula of cholesterol? Well, I can, oops, I didn't want that. Let's go up here, grab this guy, and get rid of this. So if I want the chemical formula, I say compound formula string in quotes. In a bracket. And you see I get the actual chemical formula. So cholesterol is C27, H46O. You could say instead of the string, you could say display and then you get it written with the proper subscripts. Does anybody know? So look at this molecule. So all of you have had some organic chemistry. So if I asked you to write down the IUPAC name for that, could any of you do it? Huh? All right, so let's go back to the original one, which was molecule plot. That's not what I wanted. I wanted just the molecule itself. All right. So there you have it. Can you do the IUPAC name of that? Well, it's got 27 carbons. It would be tough. I don't think I could do it. But I haven't had organic chemistry in a while, so I would expect that you would be better than I am at this. All right, well, let's go ahead. We can get it. That's the nice thing, right? So we can just ask Mathematica to give it to us. And so what we do is we say cholesterol, and then we say, quotes, then we say IUPAC name. All right, and there you have it. Is that what you were thinking it should be? 10, 13, dimethyl, 17, 6, methyl, heptan, 2, eel, 2, 3, 4, 7, 8, 9, 11, 12, 14, 15, 16, 17, dodecahydro, 1H, cyclopenta, phenanthren, 3, all. All right. We'll put that one on the final. All right. What if you want some other things? You learned about the chemical abstract service name. Well, you can get that too. So let's see here. If we put in CAS number, we get that. That's useful if you want to search using SciFinder Scholar or things like that. Okay. What about the molar mass, or as it's called here, molecular weight? (386.654 grams per mole). How about the density? 1046. Does that seem strange to you? Yeah, what are the units? It doesn't look like it's grams per mole, because that says it would be 1,000 times denser than water, which is, I mean, not grams per mole, grams per cc. Right? So let's find out what the units are. So if we put in an option here that says units, in quotes, it tells me, aha, it's kilograms per cubic meter. So I should divide that by 1,000 if I want grams per cc. Okay. If I wanted density in grams per cc, I could get it directly by saying, give me density grams per cc. And you see it's 1.046, which is a lot more familiar. Okay. How about the melting point? So cholesterol is a solid in its pure form at room temperature. Melting 147. What do you suppose the units are of that? Should be Celsius, right? But let's check. Degrees Celsius. Okay. One other thing. What if I want the heat of combustion? There's something called combustion heat. Well, that's one of the things Mathematica doesn't know. So if you needed that, you can go to Knovel or some other database and get that information. All right. There are many other things. I'll just show you a few more. We'll switch the molecule to water. So chemical data, water. Suppose you wanted to know the viscosity. We've switched the molecule, so now we have to make a new connection here, and it's 0.00089. What units is that? It's in Pascal per second, or Pascal times second, which is a SI unit of viscosity. Suppose you wanted to compare to, what do you want to compare to? We normally consider water to be somewhat viscous. What's a substance that you might expect to be more viscous? See if it knows about glycerol. Look at that. It's way more viscous. Do you know what glycerol looks like? Did somebody have a question? Yeah. All right, we'll get to it in just a second. That's what glycerol looks like. Okay, what's your question?
I'm just wondering why when you input the viscosity of water, why it's different than what it is on the notes.
Yeah, that's interesting, isn't it? It's a little bit smaller, isn't it? They might have, so these notes were made in 2010, so it could be that there might have been an error, or maybe they're reporting it at a different temperature. I actually don't know. I'll have to look into that. Thank you for bringing that up. All right. Other things. Just, you know, I don't want to bore you by showing you a million different things, but I'm just trying to give you a flavor for what kind of data you have access to directly in a notebook. Okay, so another one that might be of interest is the heat of vaporization, which is called vaporization heat, in quotes. Okay, so what kind of units should this be in? Should be in some energy units. Okay, so we get a number. But in order to be sure what units we have, we can check the units. What do you suppose the units are? Kilojoules per mole. Okay, so there are plenty of other things. I have a few more examples in the notes if you're interested. Whoops. But just going back to the documentation center here. There's a whole bunch of stuff in here that is listed, so if you want to know what you have access to directly in a notebook, you can look through here. Okay? All right, so I'm just going to show you a couple of more, and then we'll do the last part that I told you about. Okay, so there's also, I know some of you are interested in biochemistry. There are databases that can contain information on proteins, nucleic acids, gene sequences, and the like. And just a couple examples from the database called Protein Data. So if I just say protein data, bracket, bracket, it gives me a very long list of all the proteins that it knows about. Okay? So you can, these are all names of genes, and if you access one of these, you find information on the protein. Okay, so for example, if I want to get data on the protein here, the second one called A2M, if I type in the name, and you have to be patient. It gives me the amino acid sequence using the one-letter amino acid codes, which you may or may not be familiar with. You know, methionine, glycine, lysine, what is that, D and Q? That must be glutamine, lysine, leucine, etc. Okay, so that's the sequence of the protein. You want to find out what its name is. What's the name of that protein? We ask for the name. All right, it's the alpha-2 macroglobulin precursor. All right. And suppose you wanted to look at it. There are different ways to look at it, but one way that's kind of nice to look at proteins is to make what's called a ribbon plot. And so if you ask for a molecule plot of this protein, you get this nice ribbon plot, which if you've had any exposure to biochemistry or structural biology, you know how to interpret this. This thing here is called an alpha helix, and then there's a beta sheet here, and it wraps around, and then another little beta sheet over here, and a little piece of alpha helix here. All right, and you have the ability to manipulate that. So if you want to include one of these pictures in your notebook, this would be one of the ways to do it. Okay, so there's a little brief introduction into some of the databases that might be of interest to you, and whether or not you find that useful or advantageous to going out and looking at other databases and then simply importing data or typing it in. It will depend a lot on what you actually want to do. But I thought it would be nice for you to know that some of these things are accessible to you directly within your notebook. Now, the last thing that I want to show you, I hope will be useful for a couple of reasons. One is there are really educationally useful things out there on the World Wide Web that you can have access to. And if you do decide that Mathematica is going to be in your future and you want to do some fancy things, these serve as really nice examples. What you do is you look at one of these things that does what you want to do, and then you actually can get the notebook and manipulate it to do whatever it is that you want to do. Okay? So I'm going to switch over to my laptop now because we require some tools that are freely available on the web for download, but are not installed on the lab computers. Okay? Okay, I have a little technical difficulties here. Okay, well, I'm gonna let this try to wake up here in a second. So, what we're going to be talking about here is a couple of things. Okay, let's start here. Okay, so this website is the so-called Mathematica Demonstrations Project. All right? And they have demonstrations in a very wide variety of subjects. Okay? Now for us, we're in a chemistry class, so we're interested in physical sciences. And within physical sciences, we have astronomy, chemistry, earth science, et cetera, et cetera. So we can have a look at chemistry, and then there's different categories. And I'm just going to show you a couple of things that are available within physical chemistry. And let's see. I think it might be page 3. So here's one that ought to look familiar to you, because this is where I stole the image that's on the front page of our course website. I think I'm going to have to reboot my computer here. Okay. All right. So for each of these demonstrations, you're given this thing that looks like it was created in Mathematica, because it was. And usually then there's a little description down below. Okay? And this one was actually created by Stephen Wolfram himself, the guy who started Mathematica. And it's meant to represent the potential energy, electrostatic potential for a system containing 2 charges. Okay? And what you can do is you can actually play around with the magnitudes and positions of the charges with this little widget here. And you know, this is similar to widgets that we've made in class. And in fact, I was going to show you one that I made myself and tell you how it is that you can publish it so that it's a standalone item like this thing here is. Okay? So you can change the positions, and you can, you know, it's kind of cool, right? To be able to manipulate these things and see how the potential would change. Okay, so my computer is back up. So I'm going to try to switch over now and see if it'll work. Okay. Okay, let's see if we can get this to the laptop. Okay, so there's my computer. All right. Now, what I wanted to show you was a couple of more things about this. So let's see. Demonstrations.wolfram.com. So chemistry, physical chemistry, and then page 3. Okay, so here we are back to this thing. Gee. Sorry about this. Okay. I don't know what's going on here. Okay, that should be better. All right, sorry about that. Now let's see if it's going to show that. What the heck? Okay. Well, let's go back to the PC here. So the thing I wanted to show you here is, well, I want to show you a couple of things. So first of all, there's a couple of different ways that you can actually, if you like this and you want to see more how it works, there are a couple of ways that you can actually download it. Okay, so one way is to download it as this thing called CDF, which I'm not going to do. What that does is it actually takes this widget here and it gives it to you in a format that can be interpreted by a free program called the Wolfram CDF Player. Okay, and I'm going to show you that in a minute on my computer because I think it will work. But another thing that's really cool is, suppose you wanted to know, how can I make something like that myself in Mathematica? You can actually have the code. So I could say download source, and I want to save. Well, let's just open it with Mathematica. Okay? And look, now I have the notebook. Okay, it looks a little more complicated than what we did in the class, but there are a lot of things that we did. Like we used the manipulate, and then there's some plotting going on. There's the equations that define the electrostatic potential. But the main thing I want to emphasize to you here is that this is actually really, really cool if you want to learn new Mathematica tricks. Right? You see something that does, you see one of these demonstrations that does something you like, and then you find out how it works, and then you can customize. So I wanted to show you a couple more that I like. And I invite you to explore. You can see there are many, many of them. What's another one on this page? Let's go to the next page. Here's another one that we had on our course website. One that I particularly like is maybe on the next page. Nope, sorry. This one. So this quarter, we talked a lot about the Maxwell-Boltzmann distribution. And the Maxwell-Boltzmann distribution, just to remind you one more time, tells us, the probability distribution of the speeds of gas molecules in an ideal gas. Okay? And, we plotted it many times. This little demonstration here is a visual demonstration of the Maxwell-Boltzmann distribution that's a lot more interesting, because what we're looking at here, these are ideal gas molecules whizzing around in a box, not interacting with one another, and they're colored by their temperature as dictated by their individual speeds. So you see there's some slow molecules that are colored blue that are at low temperature, and red molecules that are going very warm. So you actually really do see the distribution of speeds. And this particular diagram corresponds to 0 degrees Celsius. And you can change the temperature and watch the molecules speed up and see how the distribution of speeds changes by the coloring. So you can crank the temperature up. Oops. Over here. Oops. And now things are going much faster, right? I think they are. Wait. Oh, that's right. What did I do? I probably just screwed the whole thing up. Let's reload it. Make sure I didn't screw it up. Yeah, that's right. We used this slider, all right? So now you see the guys going much faster, and a lot more of them are red, but there's still some blue ones, right? Because there's always a distribution of speeds. And the temperature tells us something about the mean squared speed, as we've seen from calculations that we did this quarter. Okay, and then there's a little story down here about this. And again, if you want, we got a little error over here, but in any case, you could download the code to see how this thing works. All right, so that's a little entree into the demonstrations. And as you see, there's many, many, many of them. And we're not just limited to chemistry. There's engineering. So let's see, what do we have here that's kind of interesting, possibly? Signal processing. Uh-oh. Okay. Oh, okay. Well, anyway, I thought this would give us some sound, but maybe the volume's turned off. Anyway, you can do things like play around with waveforms, whatever you want. Okay, so there's there are hundreds of thousands of these things, and again, I think in addition to being informative from an educational point of view, playing around with them, you learn things. They can also serve as excellent examples in case you want to do something sophisticated using Mathematica. Now, there was one last thing that I wanted to show you that's related to this. Actually, a couple of things. Oops. So on our website, you can have a link to what's called the Player, Mathematica Player website. Okay? And what you can do is you just say something about yourself here. Boy, we're having a lot of technical problems today. In any case, you choose something like I'm a student or something like that. You put in your email address, and then you can actually download this thing, which is called the CDF, Wolfram CDF Player, which has many, many capabilities, among which is it allows you to actually use Mathematica notebooks on your computer without actually buying the program. Okay, you can't create new content, new notebooks, but you can actually look at existing notebooks, which may be all you actually want to do. Okay, you can use them, you can execute them. All right, and another thing you can do is you can publish notebooks, meaning if you have a notebook and you want to create a standalone object like those demonstrations that we looked at, what you do is you go here and you select what applies to your notebook. So for example, it might be for educational purposes, and then you actually load your notebook and press continue. And what will happen is, a couple of minutes later, you'll get an email that has a link to your standalone executable player-ready notebook. And then you can use it yourself or send to anyone you want, and they can look at it with the free player without actually having to buy Mathematica. Okay, so that's what's called publishing a notebook. You don't need to have Mathematica to look at it. You just need this free player. Okay, and that's something that I did want to show you on my computer, so let's see if I can make that part work. Okay, so here I have a very simple notebook that I made. And so let's have a quick look at it here, and I'm opening it with Mathematica, I think. Boy. I don't know why everything's so slow. I was playing around with this earlier and it was fine. Okay. So here's a little notebook that I made that has something that ought to be somewhat familiar. Okay, so here's the actual code. And what this does, it just takes two hydrogen 1s orbitals and creates bonding and anti-bonding combinations. I draw the bonding combination here, call it sigma 1s, and the anti-bonding here, I call it sigma star 1s. Okay, and there's a node down the middle, you can see. All right, and this little notebook allows you to change the bond length. Okay, so here the bond length is in 2 Bohr radii, which is sort of the most optimal bond length for this molecule, which is H2+. So it's H2 with a single electron. All right, so you can actually see how the orbitals change when you increase the bond length. All right, you see the bond is starting to break as I make it bigger and bigger. Here I've pretty much broken the bond. And I have something very close to 2 hydrogen atoms. Okay? You can squish the bond length together. But the point here is not so much that this is a very exciting notebook, because it's not really. But what I can do here is I can get rid of the code if I want to make a nice demonstration, and then I would save it. So I can save it here. And then this is what I would actually load in here if I wanted to create this player-ready object. Okay, so I would browse, get that file. Oh, sorry, we're not on that website anymore. Okay. And then, after submitting it to be published, what I get back is this thing. It has the same name, but the extension is now MBP, and that tells me that it's a notebook that's been prepared for the player. All right, and I've actually downloaded the player. For free. And since I have that, if I double click on this guy, oh, it took me to Mathematica. Don't want to be there. I can actually open it in the player. Okay. Enable dynamics. Okay, so I've not opened this in Mathematica. I actually opened this with the free software. Okay, and I can now play with it. And it works. Okay. So that's basically that. All right, so just to summarize, in case it was kind of confusing because I was jumping around, you may, for one reason or another, want to look at these Mathematica demonstrations, or you may want to prepare one yourself. And so there's this extra capacity that you have using all free and web-based things that will allow you to look at the existing player-ready notebooks, look at their source code, actually download the source code for modification if you wish, and you can also then create your own player-ready documents and share them with your grandmother, for example. Okay. So that's just a little extra thing that's kind of nice to know about. Now that you've all had a quick and hopefully somewhat informative introduction to this very, very powerful program package, Mathematica, you may find some use for this in future. I hope so. So that's the end of what I wanted to present to you this quarter. And we do have some time left, so I thought that I would open the floor for any questions that you may have concerning the course, the final exam, other things. Yes?
So how many questions will be on the final exam?
The question is, how many questions will be on the final exam? At this point, I don't know, because I haven't even started working on it. But you can expect it to be roughly the length of a homework assignment, because homework assignments, I hope most of you generally got them done in class, in the lab class, which is 2 hours, and that's the same amount of time you'll have for the final exam. Okay? And just to reiterate, you can expect to have things from, throughout the quarter. So it's cumulative. Obviously, I can't ask you to do a little example of everything we've done. You won't have time. But there's some things that we've done that I think are important. Like, you can certainly expect some curve fitting. You may have to use the solve command. You may have to do some derivatives and integrals. Maybe make a couple of different kinds of plots. The kind of stuff that you're going to be most likely to use in physical chemistry class. Any other questions? Yes?
I just was wondering, so where, again, in the website, is it in the website where you publish your notebook and get the CDF?
Okay, I'll show you once again. I know it was jumping around. Okay, so I'm going to go back to the PC here. Okay, so if you either Google, Mathematica Player, or if you go to our course website, I put a link to this website. You get to this website here, wolfram.com products player. Okay, and then what you can do here is you can actually download that, okay, on your own computer. All right. Now, if you want to take a notebook that you've created and make this standalone version that you can interpret using this thing, then what you do is you say, I want to publish. Well, this is one place where you can get to the publisher. And then what you do is you say, what's the point of your publication? And I would suggest you don't do commercial distribution unless you really want to sell it. And then you browse your notebook. Okay, so we don't have one here available, most likely. And when you say continue, it probably won't let me continue because I didn't put a name. Yeah, please use browse. Well, let's just see if we have something here. We're safe here. Do Do we have anything here? I guess we could use this one for fun. I don't know what it does. Okay, and then I say continue. Oh, okay. I have to select the use, browse, open, continue. Now I have to put in my email, re-enter, put your first and last name. You don't have to say your organization. You don't have to say hello to the people at Mathematica. And then you press this button, Convert Now. I'm not going to do it because I don't want to get this thing. And it will send you an email with a link. And when you press on that link, it will download your player-ready object. Okay? So that's kind of nice. And then you can email it to your grandmother. Right? Or whoever you want. To me, you can show me what great things you did with Mathematica after this class. All right, any other questions? Going once. Going twice. Gone. Okay, so we'll see you, I guess, a week from today, right, at 1:30 p.m. And like I said before, if you want to study, just look over the notes, go over what we did, and remember what it is that we did so it won't look strange when I ask you to do it again. Okay, so long. See you next week. Thank you. Thank you.